Hey everyone, and welcome back to the channel. I'm a little bit sick this week, so I'm going to try and make this one a bit fast. Today we're going to be talking about Dapper, which is a distributed tracing framework. Now, I personally have also tried to adapt distributed logging and tracing into my life in the sense that I distribute the logs that I take at the office into a variety of different bathrooms so that no one can trace them back to me. So already I've learned a lot from this paper, and I've really gotten a lot out of it. But anyways, let's go ahead and go through it and see what Google learned. Let's get into it. Okay. Dapper is a paper out of Google in 2010, and basically the reason we want this type of thing in the first place is that Google has a very interesting computing environment in the sense that it's completely distributed, right? It's a lot cheaper to run these massive programs on, a bunch of distributed machines that run commodity hardware as opposed to like one massive supercomputer or something like that. So the problem with that is that all of these machines are making a bunch of RPC calls between one another. And so actually figuring out where those RPC calls are coming from, what machine they're originating from, where they're ending up, when they get there, when they get back, that becomes a very tough problem because you have to instrument every single program that's running everywhere. And basically the solution that Google ultimately wants to deploy has to satisfy a few different properties so that it will work well. Basically, first off, it needs to be ubiquitous. For the non-native English speakers on this channel, that just means that they have to be common, right? So it's not enough that they run on a subset of the services, even if it's 80% of them. That means 20% of your RPC calls or threads or things like that aren't getting traced, and you're lacking a serious amount of data, which is not going to be acceptable. Number two is that they need to be performant, right? At the end of the day, if we want this thing to be common, we need to be running it everywhere. And if it has to be running everywhere, that means it has to not be having a huge performance hit, even on our most popular applications like, say, Bigtable or GFS or something like that. And then finally, it should be transparent to developers. This kind of is another step of making it common within Google's deployments, but if every single developer has to add some extra configuration or an extra snippet of code to get this thing running, it's ultimately not going to be a success. Ideally, this should have to be running or be able to be running with zero extra code. And so that's what Google is able to do by using Dapper. So just to quickly show off what a trace is in general, because it's not a term that necessarily everyone's familiar with. Maybe you've heard of a stack trace. It's kind of a similar idea, but in this case it's a distributed trace, right? So what they're really trying to map out are a bunch of things like RPC calls between a variety of components in a system. So maybe we start out with some front end and we're mapping out RPC call number 1. So that's going to go and hit, we've got trace ID X over here. So, we start out and everyone has a trace ID. So this is considered one span within the trace. The span itself has an ID, and then it may also have a parent ID because keep in mind that when it comes to these distributed systems, we've got tons of microservices, and within each microservice, we might be making RPC calls to other microservices. So the whole value of Dapper, or a utility like Dapper, is being able to track all of those nested relationships. So you might have one span right here and an RPC call from it. And then right off the bat, maybe that is actually calling another endpoint. So maybe, we're hitting the back end of our system, and the back end is calling some endpoint RPC2. And then again, note that this has now the same trace ID so that we can associate them later, but it has a different span ID because this is the span this time. And then the parent ID is actually going to point us right back up here so that we can kind of traverse this graph or this tree of spans to make an entire trace. And then similarly, maybe we've got components like caches and databases. And so, each of these spans, again, has a trace ID. It's got, an ID of its own, and it's also got a parent ID so that we can, recreate this entire thing in like a GUI or a web UI or something like that. Cool. So what does an actual span have in terms of the data that's being persisted? Well, there are a few different things, right? So each span is probably representing an RPC call. And so if that's going to be the case, definitely it's going to have something like the time that a client made a request. It's going to have the time that a server that was serving the RPC received that from the client. It's going to have the server response, so when the server is starting to send out that data. And it's also going to have the actual client receive time of the response. Now note that these are distributed systems, right? And so the client and the server are probably not on the same host machine. And so if that's the case, we may have some clock drift between the two of them. And so what you may actually see is maybe the server receive is over here and the server response is over here. That being said, we can take advantage of the fact that we know that, just causality-wise, the client request must come before the server receives the request. And so, we can kind of offset those timestamps a little bit back. and make sure that everything's looking proper. And in the same sense, this server response has to come before this client receive. So even if we're not completely perfect on the real time that these things happened, we can kind of offset the event times such that they are, at least sensical. Another thing to note is that developers can add custom annotations in their code. So even though the goal is to be able to, implement Dapper in your system with 0 additional code for the system's developers, it is going to be the case that you can annotate or add metadata to these spans. So for example, these can have, just like key value pairs. So maybe you're going to say, oh, there's a cache miss here. Or maybe you're going to say, hey, here's a timestamp that some event happened. So in this case, maybe on our cache, we're grabbing some sort of lock in order to get a piece of data. So there are a couple of different types of distributed tracing. Google evaluates both of them, and ultimately they choose one. But basically, there's black box tracing, where black box is saying, okay, in your RPC calls, you're not adding any additional information whatsoever to each RPC. You're not adding any additional headers or any data in the body or anything like that. Instead, we're just going to use, things like the timing of the RPC call and, maybe some other additional information about, where it's coming from and where it's going to in order to try and associate RPCs together to figure out which ones are, nested as part of some other. That being said, that's going to be tough because it requires you to have a lot of data, and collecting a lot of data means it's going to take more of a performance hit on your system. So instead, what Google chooses to do is do something called annotation-based tracing, which is basically every single span within a trace shares a trace ID, right? So I demonstrated that 2 slides ago. And the reason they can do this so easily at Google, the reason they can roll out Dapper so easily in general at Google, is they have this very homogeneous computing environment, right? Pretty much all the applications at Google, and I can confirm this is still the case from having worked there myself, pretty much use a ton of similar libraries, right? Like if you're making RPC calls, you're probably almost always using gRPC. For threading stuff, there's very similar libraries, and for callbacks, there's similar libraries as well. And so basically, the Dapper developers really only have to change those libraries, and they can make this transparent to pretty much everyone who uses these libraries within their services, and it's super easy to roll out. So fortunately, they have kind of an environment where they can roll out a system like this fairly easily. So just to elaborate on those a little bit more, basically there's a threading library, right? So, every single time that you're running a thread, you now have a trace context associated with that thread, which is probably just something like the trace ID, the current span ID, any annotations that may have been stored with it. Similarly, if you do any amount of asynchronous work, pretty much everyone at Google uses the same, core callback library, right? So if I make an API request, when I receive a response for that, it's going to be handled on some callback, probably in some sort of thread pool internally. But when I actually, create the callback in general, I'm going to pass it my trace context so that it already has the trace ID to basically continue to annotate that trace and, make more spans from it. And then finally, like I mentioned, everyone's probably using gRPC or the same RPC library in general. And so what that means is that, if you're using the same code to always make endpoint requests from one Google component to another, you can include that trace ID, you can include that current span ID, and then systems are able to kind of add data to them regardless of where they live or what host they're on, which is really, really nice. Okay, so let's go over the actual Dapper architecture itself. This is going to be probably the most complicated slide in this video, but even then it's still fairly simple. This is a simple paper in general, and I like it a lot. So I'm going to basically, draw a little dotted line right here because the idea is these are just, all typical Google services, and then co-located on them is stuff, related to Dapper, right? So let's say we've got some front-end server, maybe there's a back-end server, and then maybe there's a database. So those are running on 3 distinct hosts. And of course, on each host, there's also just going to be a local disk. I draw them as a database here, but I really should have just drawn them as a local disk. And then on each one of those, you've got these small, pretty inexpensive processes running called Dapper daemon processes. And so basically, as the front end, back end, and database are running, they're logging a bunch of data that, is happening because they're making RPC calls, or they're making new threads, or they're making callbacks, or things like that. And they're logging them to disk. And then really all that happens is the Dapper daemon is sitting right here as a very inexpensive process on that machine. And so when these other, distributed services called Dapper collectors come by and go to each host and say, hey, do you have any more data for me? The Dapper daemon is exposing an endpoint to basically serve that data over the network and return it back to the Dapper collectors. And so once we do that, the Dapper collectors then take that data and write it to Bigtable. And that's basically our main way of exposing all of this tracing data for others to read. Now, there are a few fine details right here. So for starters, the Dapper daemon generally makes it so that data is, in the Dapper collector every 15 seconds or so. There's some long tail latencies there where it could technically be up to like 2 hours, they mentioned in the paper. But, the data is being served not instantly, but pretty close to instantly, which is very, very good. Another thing to note is that if you look at the actual big table schema itself, so a couple things. One is that every single trace is organized in the following. We have our trace ID, and then we have every single span as a row within the trace. Because keep in mind, Bigtable doesn't necessarily force you to use a certain schema. You can have an arbitrary number of spans associated with a given row, which is very nice because it just means that one row is representing one trace, so you get good data locality out of that. Another thing to note are these three columns right here, the process, the host, and timestamp. So actually, although you can technically search up a given trace by its trace ID very quickly, the authors of the paper mentioned that they make an auxiliary index on the Bigtable based on these three values, right? Because let's say you're running a certain process for a team called process X. Process X may be slow. So you're saying, all right, is this a recent pattern that process X had been slow? Well, first I'm going to look for process X in the database. I'm going to choose a couple of hosts where I notice there's been some sort of performance degradation. And then I'm going to look at a timestamp of all of these traces to try and get a sense of, hey, is this a recent issue? Did this maybe get introduced with one particular code change or at one particular time, so I can associate it with a code change? So you've got a common way of searching things, and so ultimately they made this index in order to make that way a bit faster. Now note that all of this trace collection is performed what's called out of band. So one option that in theory you have when you're making requests like this here, so I'm going from the front end to the back end to the database back to the front end. In theory, you could include all of the current spans within a given trace over all of those RPC requests, aggregate them first in the back end, pass them to the database, aggregate them again on the back end, and then pass them to the front end, and then it's just the front end who uploads directly to Bigtable. So that is possible, right? But the problem is these traces can actually get decently big in size if they have a lot of spans in them. And so it gets to a point where the trace itself would actually just be making the RPC, significantly bigger compared to the actual RPC payload. And so it doesn't even make sense to do that. Instead, it's better to kind of disaggregate this collection process, right? Where every single host is responsible just for the data that's collected on it. And then the way it gets aggregated is by basically just putting it in the proper Bigtable row. And that's where we're kind of joining all of these spans together into one single trace. Okay, so another aspect of this problem that's pretty important is sampling. Like we mentioned, some Google servers are really performance sensitive, and they wouldn't want to roll out Dapper if there were any concern that rolling it out was going to really slow down the performance of that machine. And so basically what we can actually do is perform sampling, right? We don't necessarily have to take every single trace of RPC calls, but rather we can just take a percentage of them. And so basically for servers that are deemed to have enough load, the authors of the paper ran experiments, and they found that just sampling 1 out of every 1,024 traces was actually enough to get a really good sample size, right? Because generally speaking, if you have enough load on a system and you're getting thousands of requests a minute or even more than that, something that comes up once and is slow is going to come up a few thousand times, and so you only need a few traces to capture that information. It's totally fine if you get 1 out of 1,024 samples. At the same time, they noticed that, at 1 out of 1,024 samples, it's very, very clear that there's no performance impact, whereas if you did something like 1 out of every 16 traces, there was still technically a noticeable performance impact. So keeping it to this number was very, very good. That being said, if you are a service that has a particular low load usage, right, so you're an unpopular service and maybe only get like 1 request per minute, taking 1 out of every 1,000 samples is not going to be good because it means you're going to lose the vast majority of them and you're not going to have data. So one thing that they actually want to introduce in the paper is something that they call adaptive sampling, where basically rather than having every single service owner configure the rate at which you're doing sampling of traces, instead what they'll do is just have a target trace output or trace collection rate or trace generation rate. So in this case, maybe they're like, oh, I want to generate 1 trace per second. Depending on how much load you're getting, that means you're changing your sampling rate adaptively, which is very good because it means that no one has to configure anything. Not only are they doing trace generation sampling, though, they're also going to mitigate the throughput needed by Bigtable, right? Because even if we're still doing a lot of sampling, at the end of the day, we may publish a ton of rows to our Bigtable if we just have a ton of servers, and they want a way of basically saying, shoot, Bigtable's in trouble, let's slow down the amount that we're actually publishing to it, right? So if you recall, we have all these Dapper collectors right here that are doing the publishing to Bigtable. And so what they do instead is they introduce a second parameter that is specifically used on the Dapper collectors that perform sampling there. So first you get the data from the Dapper daemons on the actual hosts themselves, and then in the Dapper collectors you might sample down data a little bit further to reduce the load on Bigtable. That being said, keep in mind that on the Dapper collectors, you only have individual spans, right? Or you might only even have part of a span. You might not even have a full span. And you certainly don't have a full trace because the Dapper collectors themselves are just reading from a host at a time. And keep in mind, we're doing this whole out-of-band collection thing. So we don't have access to the full trace at once. So how do we sample in a way such that we're making sure that we're keeping full traces and, throwing out full traces? Well, the way that they do that is they just sample based on the actual trace ID itself. So, you can take a hash of a trace ID, hash it to some value between 0 and 1, and then keep it if, it's between 0 and some number p, where p is going to be the sampling factor. So a pretty clever solution to do that, makes a lot of sense, and it keeps data intact. Okay, so kind of unclear slide in retrospect, what I meant, but I'll explain it right now. I guess the question is, how do you use something like a distributed trace effectively? Well, I guess the main idea here is if you're an engineer at Google, you're responsible for a very, very small amount of software relative to the total amount in the company, right? So you may be responsible for like one endpoint or a couple endpoints on a front end, and then, there might be a back end, there might be a database. Who even knows what's going on within the database? That's not your domain expertise. And so if you're trying to figure out where the latency is coming from in your application, something like Dapper is really, really useful because what you can see is actually all of the API requests that are being made. So you may think, I'm making a backend request, and then that backend request is going to a database, but maybe the database is making a few different requests that you didn't realize were happening. So being able to kind of get this whole network topology lets you realize, hey, maybe there's some extra API requests going on that I couldn't have previously been aware of because I wasn't even looking at that internal code. And then, you can reach out to the other engineers, you can read the code, see what's going on, and so it's just good in terms of getting better awareness. Cool. In addition to, literally just looking at the critical path of a service and, figuring out where there are extra calls or work being done that isn't necessarily needed, there are plenty of other unforeseen benefits that came out of Dapper that the Google authors like to outline. So number one is just enforcing security, right? If we're, trying to make a secure application, there are definitely a few certificates that we have to check, and using Dapper can ensure that we're actually performing those checks. There are probably also similarly some other applications that we should not be reaching out to. For example, if you're exposing user data or something like that, there are probably certain parts of the Google infrastructure that you shouldn't be talking to, and this can prove that you're not doing so. Number two is resource accounting, right? If you've got some sort of database and you want to figure out which applications within Google are hitting them the hardest or sending the most RPC requests there, this is going to be really effective for that because you can take the data in Bigtable and you can run something like a MapReduce job over it in order to kind of aggregate who's making the most requests. Number three was they just said there was a random analysis being done over the best RPC compression strategies. So the way you would do that is you look at all the spans that are making RPC calls, you annotate them with the type of compression that they're using, and then again you run a MapReduce job over all those spans and check how the timing of every single RPC request compared based on the compression type. Unnecessary reads to master nodes. So if we have a database, right, and we've got a master node and then we've got a couple of follower nodes, sometimes it's going to be the case that we're reaching out to the master node when we don't actually have to, right? Because obviously reaching out to the master is typically going to be slower than reaching out to a replica because the master is also handling writes, and so generally it has a lot more load on it. So if we can ever take off load from the master, and it's not going to necessarily impact our correctness of our application, we want to be able to do so. So by exposing that we're reaching out to a master node in a particular endpoint, we can again make the conscious decision to move that request to a replica node. A better understanding of cross-cluster network topologies. Basically, the idea here is that, when you have two different data centers and they're communicating a lot between them, the link can get saturated. And so sometimes you can figure out, hey, I see that it's these two hosts in particular that are really communicating with one another. But using something like Dapper traces or Dapper spans is going to allow us to tell, oh, not only is it these two hosts, but it's this particular application on these two hosts, and within that particular application, it's this particular RPC call. So that's going to allow you to really root cause the issue a little bit easily, a little more easily. And then finally, just this concept of identifying clients with more load in, shared or layered storage. So something like Bigtable at the end of the day, you can get a sense of kind of which applications are hitting it, or maybe even which tables are being hit the most. But it's hard to tell which particular clients are hitting that table the most, and this is going to allow you to identify that and then call out bad actors in shared storage. Okay, there are a few things that Dapper, despite solving somewhat well, is not perfect for, and so let's go ahead and outline those as well. Number one is this concept of amortized work, right? So a lot of systems will make requests in batches. If I'm uploading data to a database, I may do it asynchronously, and I may do that in a batch of writes, right? So the reason I do that is because there's lower overhead. That being said, it's hard to trace that type of thing because it's asynchronous, right? We don't account for it in our initial RPC call to, say, the backend that's uploading data to the database. And so, it doesn't really give us a sense of the latency that's going on there. And maybe it's not asynchronous. Maybe it's just, we keep all these writes batched, and then for one particular RPC call, that's when we do the entire batch write. Now that entire RPC call looks super expensive when in reality we were just amortizing a bunch of work. So it's hard to really keep track of that. You kind of need application-specific logic there. Number two is going to be batch workloads in general, right? Dapper is very much made for the type of OLTP situation where you're making a request to an endpoint that might be making a few different requests to other endpoints, and we're tracking all of those one at a time. That being said, for batch workloads, kind of the thing here that you want to trace is the performance of every single initial data input and kind of all the systems that it's going through, how it's getting passed between them, the latencies there. So it's just not originally built for that. They definitely did build profiling tools for these types of things, but it's not going to be Dapper. And then also just within an application, maybe, for example, you might say, okay, I can see that this particular RPC request is slow. That's really all you can figure out, right? Maybe you annotated some more things. You can figure out more information with that. But, just kind of vanilla Dapper, you're not going to be able to figure out the root cause of why something is slow necessarily. So for example, one that they gave in the paper is within an application, how can you tell whether this RPC request is slow because of queuing delays, right? So too many things are queued up in a queue, and so it's taking a while for that particular computation to run. Well, one particular solution would be to basically have two traces at a time, or print out two traces at the same time, and as a result, if they're both slow, then maybe it is due to queuing. But the point is, you just need to write all this additional logic for all of these edge cases, and they want Dapper to be as simple as possible and easy to deploy, and so ultimately it's not really for this type of thing. All right, well, in conclusion, the big value add of Dapper is going to be its ubiquity. It is deployed on virtually every server in Google, and as a result of that, you get really, really rich metrics that you wouldn't have been able to have otherwise. Dapper could have been made a tool that, provided more metrics per trace or per span or something like that, but then maybe it would have had more of a performance hit, maybe it would have been harder to roll out for everyone, and so if only 50% of the applications in Google were using Dapper, it wouldn't be nearly as useful. The value comes from being able to trace an entire RPC call through pretty much every system within Google's distributed cluster. The reason we can do this in the first place is because Google uses all these homogeneous libraries. In certain companies where you can kind of just use whatever tooling you want, this is probably going to be a lot less feasible, but it does give kind of a blueprint for how companies should go about laying out their technology so that you can eventually build systems like this. Ultimately, especially in a company where you've got so many developers that one person can just have absolutely no idea what's going on within another service, being able to kind of trace all of these API calls or RPC calls throughout a system is very, very valuable. Anyways, guys, I hope you enjoyed this video. For what it's worth, I think I may be going on an interview on Hello Interview on this Saturday, so probably when this video is coming out. So I hope you guys take a look, and I will see you in the next one.